The work of Ronald Fisher is within a tradition of researchers who were interested in evolution by natural selection and inheritance, and they developed statistical methods in order to study that phenomenon. The founder of that tradition was Francis Galton, who was the cousin of Charles Darwin, and Galton made contributions not only to statistics and research methods, but also to psychology and other areas. That tradition was continued by Carl Pearson, who developed things like the correlation coefficient, the chi-square test, but we're going to skip one generation and we are going to go to Ronald Fisher, who was born in 1890 and died in 1962. And Ronald Fisher was the most influential of statisticians, at least in the social sciences, but if not in everything. And we are going to see how he developed a statistical significance and, in general, what was his contribution to statistics. So let's start with his book published in 1925, Statistical Methods for Research Workers. In that book, he defines what statistics is. And he indicated that statistics, the topics of statistics, the areas of statistics are three. One is the study of populations. Second, the study of variation. And the third is methods for data reduction. In terms of populations, I will introduce this entity called the probability demon. That's not something that Fisher proposed. That's my contribution. And the probability demon is an entity, an imaginary entity, a hypothetical entity that deals with samples, populations, numbers, and tests. And I will introduce this because I think it's a way of honoring the work of Ronald Fisher. Fisher says a lot of things about populations that most researchers in psychology don't understand. And the first one is related to populations. Populations for Fisher are abstractions, not reality. That's why I introduced the probability demon, and I'm going to use this poetic license I'm using later on in this lecture. So for Fisher, if we measure height or IQ of 10,000 people, the population that we are interested in is not the 10,000 individuals. The population that we're interested in are the 10,000 values. So the populations that Fisher is talking about are populations of numbers. He was the main proponent of one of the schools of statistics, which is the frequentist school, as opposed to the Bayesian school, which I follow. And he proposed that if you measure something towards infinity, so let's say you take the measurement of one person, and then you take the measurement of another person, and then another person, and you do that towards infinity. So this is, we don't have infinite number of people. We have finite number of people, but that's why he's talking about an abstraction, a hypothetical thing. So a population of values of height is a hypothetical population of infinite number of heights. So that's the frequentism. We need to talk about a long run. A huge amount of frequencies, but not a huge amount of frequencies, an infinite number of frequencies. And one thing that is very important and we tend to forget, for Fisher, is this the same whether we apply measurements, infinite number of measurements in one person or in different people? We will have a population of measurements. So that's why it's important that we talk about populations of values and not populations of people. And regarding samples, something interesting in Fisher and understanding this solves a lot of problems, is that every single value that we have, so let's say we take one measurement, we take the working memory capacity of a participant, just one. He claims that that should be considered for statistical purposes as one value that comes from a population of values. And also, he adds the word random. It's a random sample. In this case, it's one value, so it's a random sample of one's size. The size of that sample is one, only one value. He says it's a random sample, and a random sample means that, let's imagine this population of infinite number of values, and we take one of those values randomly. And that's the measurement we obtained. So we obtain a random sample from a population. And why is this important? It is important because if we know the characteristics of the hypothetical population, then we can determine the probability of observing the data we collected. We can even calculate the probability of observing any possible value if we know the characteristics of the population. The second topic which Fisher considers as being part of statistics is variation or variability. And until Galton, variability was considered an error. So people were thinking that there was something that sort of a magnet towards the mean of a distribution, and things that are far from the or away from the mean of the distribution, that's considered error. Whereas after Galton, or since Galton, researchers started to consider variability in itself as some phenomenon of interest. And therefore, the statistics is also about how things vary. And that leads to frequency distributions, which is to collect data and you observe values, and those values are distributed in certain way. So more you observe more values within some interval of possible values, or less values in another interval, and so on and so forth. So you create what is called a frequency distribution. The third aspect of statistics is data reduction. And what are the problems of data reduction? One of the problems is specification, which is, given a data set, I've got a lot of values, I collected data and I have these values. Well, what distribution best specifies that data? So, is it a normal distribution? Is it a uniform distribution? Is it a binomial distribution? What distribution best specifies the data? So that's one problem of data reduction. And typically, a very common and popular way of data reduction is to obtain the mean of the distribution. And that is a very important, very useful data reduction summary. So of all the data points you have, you come up with one value. and that's the mean. But you lose quite a lot of information. You can add more information by providing the standard deviation, which gives you an idea of the dispersion of the values away from the mean. But sometimes you need more than that, and you need the whole distribution that will give more information. So there is here a balance between knowing all the data, but you may have thousands of values, and this is not practical to deal with all those values. Or you reduce that data into just one value, the mean, two values, mean and standard deviation, or you provide a bit more information, which is the distribution. But all these, either the mean, the standard deviation, and the distribution, are ways of data reduction, because you are not considering the whole data. You reduce the data into pieces of information that you can work with. The second problem of data reduction is estimation. And that is the problem of deciding what statistic we should use to estimate parameters. And here we've got two very important terms. One, the term statistic, which is a technical term that is different than the statistic as a discipline. Statistic means, in this context, some measurement that we have of the sample of data we collected. So the mean is a statistic. The standard deviation is statistic. We have a percentile is a statistic. The median is a statistic. Or the sum of all the values is a statistic. We don't use that statistic very frequently nowadays, but it's a statistic as well. So any characteristic, some value that we come up with about this sample. And the other term is parameter. And parameter is the same idea of statistic, but parameter is about a population. So what's the mean of the population? What's the standard deviation of the population? So these are parameters of a population. And when we talk about estimation, we talk about induction. So we observe a sample of values. It's a limited amount of values. We don't observe the whole population. So we make an induction from the values that we have to the population, which would be the hypothetical population of infinite number of values. And the third problem of data reduction is the problem of distribution, which is a bit confusing, because we talked about distribution when we talked about specification. In this case, Fisher is referring to the deductive part of this. So basically, if we know the structure of the distribution of values of infinite number of values, so a population, and how we deduce what possible values are there. And when he's talking about this, he's also talking about the estimates of the parameters. An estimate is another technical term that is very important. An estimate of a parameter is this. For example, we have a sample and we are interested in estimating the parameter of the population, one parameter of the population, let's say the mean of the population. What shall we use as an estimate? So given the sample, what shall we use in this sample as an estimate of the mean of the population? Well, the answer to this is not straightforward. In this case, statisticians found out that the best estimate of the mean of the population is the mean of the sample. But in other cases, it's not exactly like this. Like, for example, the best estimate of the standard deviation of the population is the standard deviation of the sample, but calculated in a different way than the standard deviation of the population. We're going to see that later, but so the estimate of a parameter is not necessarily the equivalent in the sample. So let's illustrate what I was talking about, the process of deduction and the process of induction. So let's say we've got a probability distribution, or two in this case, and the two distributions here are normal distributions. So in this case, we've got a normal distribution with a mean of 30, and in this one, we've got a normal distribution with a mean of 80. So now, when we know that, when we can make a deduction of what's the probability of observing a specific value. So from this distribution, so we assume that this distribution is how the values in the population are distributed, and what's the probability of observing these values here. So these bars there are you collect data and you obtain these values. So this is the data. And because we already mentioned, we consider that a random sample. In this case, it's a random sample of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 values. But as I mentioned earlier, it could be as low as one value. Okay, so given that distribution, what's the probability of observing this value? What's the probability of observing this value? And this one, and this one, and this one, and this one. Now, I can do the same with this one. What's the probability of observing this value, this value, this value, and all of them? So, in this distribution, in the one on the left-hand side, values that are close to 30 are more likely than values that are far away from 30. And in this distribution, values that are close to 80 are more likely to occur than values that are away from 80. But if we say, given this distribution, we say this distribution is the true distribution of the population, well, we can establish without any problem what's the probability of obtaining any of these values. Now, the problem arises when we talk about induction. Induction in this sense is very, very difficult. Induction is the opposite process. We've got the sample, these are the same values, and now we need to decide from which population do they come from. So we don't know what's the population they come from. And we need to decide, do these values come from one population of values, or they come from two different populations of values? And so basically you can say perhaps, well, these values here, they are very probable from a distribution that with a mean of 30. This one, they're probable from a distribution with a mean of 80. But it's very complicated. It's more complicated than that. We are talking about this distribution with mean of 30 and mean of 80 because I showed you that in the previous slide. But when we do research, we don't know. We don't know the characteristics of the population. So it could be that this comes from one unique distribution with a mean of 55. Or it comes from two distributions, one with a mean of 30 and one with a mean of 80. But why we say 30? Why not a mean of 35? And the 180, why not a mean of 85? It could be anything, actually. It could be from distributions that have different means. So that's why the induction, so from the some values we have to make an estimation of the characteristics of the population from which these values come from, it's very tricky. It's very, very complicated. And that's what divides the two schools of statistics. The frequentist, which is Ronald Fisher is main exponent, and the Bayesian, which have different solutions to this problem.